Alright guys, so today we're doing lesson 1.7, which is on domain and range. This is the classwork that you should have. If you don't, make sure that the substitute gives it to you guys. Looks like this, 2 pages, 3 pages. So that should match with these notes that we're going to do today. Um, we're actually in Unit 1B now. We're done with Unit 1A. So when you go into Schoology for the homework and whatever, make sure you're in 1B. Um, so this is today's lesson is pretty much about functions, specifically with domain and range. So domain and range of a function, that's the first day. We'll do another day of this. We might just be able to do it one day. We'll see. But everything that you'll see now, instead of having y equals something, we're going to work with functions for the rest of the unit. So it's function notation, simply just to replace y with f of x, just saying that, basically the resulting value is a function of whatever you plug in for x, right? Whatever results is derived exactly from what you plug in for x, right? So it's still the same thing. They're both lines. They mean the same thing. Just use function notation instead of y. Okay. So domain and range kind of correspond with x and y. Um, the domain, when I want you to think of domain, I want you to basically say, what can I plug in for x? And that's really what domain means. So we're going to write that in there if you have a blank on yours. All right, so what can I plug in for x, right, in the function notation, right? Most of the time it's everything, but there's certain things that you couldn't plug in with certain functions, which we'll get into today. Um, and then, we call that an independent variable. It's independent. It does not depend on the range. In fact, the range depends on what you plug in for x. It is a function of the x value that you put in. So the range basically says, how I want you to think of range is what results, right? So range results. They both begin with R, right? So domain, what could I plug in for x? And then the range is what results. And that's typically what we call the y values. Or we can call them the f of x values, right? Because we kind of replace y with f of x. It means the same thing, right? So if you think about, as we go through the slides, or even before you continue, critical thinking questions, what types of functions, right? What types of numbers or things out there that exist in math would have domain restrictions, meaning, you wouldn't be able to plug in everything for x because it could create a problem, right? And we'll go through that and we'll identify a couple. But before we do, we're going to use what I call, or what's called interval notation. Sorry, I got this slide first. All right, so graphically, domain, right? The question you kind of want to ask here, because domain deals with x values, right? And this is the x-axis. So it kind of works left and right. So when you have a graph and you're trying to identify the domain of the graph, if you have a visual of a graph, you don't have to say, what can I plug in for x? You're more looking at the graph itself. You're probably thinking, where do I have graph? And from left to right. So left to right, right? Because that's the x-axis goes left to right. So you're basically looking at where you have x coordinates when you're looking at a graph and trying to figure out the domain. And then the range, right? The range, which is the y values. And there's our y-axis. That's kind of where you're saying the same question. Where do I have graph but from the bottom on up, right? Right, or from bottom to top, right? So, I could give you a picture of anything. This is like an absolute value graph right there, right? So if you're trying to figure out the domain of it, you figure, okay, where do I have graph from left to right? Do I have graph over here? Well, left to right, yeah, you would, right? You would have graph. Like this x coordinate right here would have a graph. It would be like way up there. But you can see if you extended these arrows, you would have graph all the way to the left, and you would have graph all the way to the right, right? Those are going to exist everywhere. That's all the way to the right. So you have graph everywhere from left to right. However, from bottom to up, which is really the range, right? Where do you have range, or where do you have y values? Right? You'll never have y values down here, right? These y values on that y-axis are never going to get hit, because if you look at the shape of that graph, the lowest point that you'll ever have is right there at that vertex. You'll never get lower than that. So the range would actually be restricted, right? The lowest y value you would have is like, you know, whatever like that is, like -2.5 or something like that. Like that would be the lowest y value. And then it goes on up all the way, you know, to infinity. So that's kind of how you can get domain and range from a graph. You know, look left and right for x values and look down and up, down to up for y values. And you can usually identify domain and range from a graph. But I still want you to be able to do it algebraically just by making sense of, you know, what the equation is, which we haven't seen equations yet. But when I tell you to express domain and range, it is a little different in Algebra 2 than it was in middle school. Or any type of inequality is going to be this way. We're going to use something that's called interval notation. Just a different way to basically express an inequality, right? So before, you probably had something like x, you know, is greater than or equal to 0. That's expressing an inequality. It means all your x values have to be bigger than or equal to 0, right? We're not going to use that anymore. That is what we called set builder notation. Right, so those x is greater than with those symbols like that, that's called set builder notation. I may ask you that from time to time, but for the most part, we're going to be using interval notation only. It's really what you use in pre-calculus and calculus too. So I'm going to give you some definitions which should correspond with your classwork. Just kind of know them for now, and then we'll actually work with them, and you'll be able to make sense of them later. But basically, if the numbers are going to go all the way to infinity, like x is greater than 0, that would be every number that's bigger than 0 all the way to infinity or equal to 0, right? So we use an infinity symbol for an infinity, and if it went to negative infinity, like if it was less than or equal to 0, that would be 0 would be the highest, negative infinity would be the lowest, which was actually where you'd start. So those are the two symbols we use for those two. We also use these other symbols, which are just parentheses, to kind of separate numbers out. So parentheses, if you're going to use parentheses, it means it cannot be those numbers. It's the same thing as a less than or a greater than sign, because those numbers do not include those, right? So if you said, you know, y is less than 3, you can't include 3. We would actually put a parenthesis around the 3, and I'll show you what they look like in a second. But basically, that would be the same thing as a parenthesis. Now, if it was less than or equal to, oh, and there is a note here. A general rule of thumb, if you're going to use the infinity or negative infinity symbols, always have a parenthesis around those. That's always going to be the case. You can never put what's called a bracket around those, which brings us to brackets. So brackets means it does include the number, which is the same thing as a greater than or equal to, or a less than or equal to. So if it could be that number, you're actually going to use a bracket instead, right? So again, if it was y is less than 3, or equal to 3 actually, y is less than or equal to 3, we would actually put a bracket. We would be using a bracket in that scenario. And again, it probably seems confusing. What are we going to do with these? I'll show you in just a second. But just kind of keep these things in mind. And then sometimes you see the word or in set builder notation, right? If you have x is less than or equal to -2, or x is greater than 3, greater than, okay, there we go. We've seen that before. That word or, we're actually going to replace with something called a union, right? And we're just going to use the letter U to basically separate things instead of or. It just means in union with, same thing as or. And that's it. So those are all inequalities. I'll show you what we're going to do with them now. So let's say I wanted to, let me just give you an example, right? Let's say I wanted to put this inequality that I just had into interval notation, right? So I got to think, okay, x is less than or equal to 2. You can put it on a number line if you want. Say, okay, -2, it includes -2, so I'm going to use close, and it's everything this way. And then greater than 3, all right, there's 3. I cannot equal 3, so I'm going to use an open circle, but I'm everything bigger than 3. So that's what it looks like on a number line. So you got to think, with interval notation, we start from the left side and we work to the right side. We always start with the smallest possible value and work to the biggest possible value. So if you think about how far does this arrow go? Well, this arrow goes to -infinity, right? That's going to go on and on and on forever. So that's what we're going to start with. So as I said before, anytime we're going to use a -infinity or a positive infinity, we need to use a parenthesis around it. So that's what we start with. So we're at -infinity, and where are we going to go into? We're actually going to go into -2, because that's where it kind of stops. So I just put a comma next to it, and then I put -2, right? And then you basically say, okay, can I equal -2? Yes, I can. It's a closed circle. I can be less than or equal to -2, so I'm going to use a bracket. And that means every single number that is less than or equal to -2, right? -infinity to -2. Now there's a separate chunk, which is this, so I need to use a union symbol. Basically say that it could be something else. And this one is 3, and it starts at 3, but it cannot include 3. So I'm going to use a parenthesis, because parenthesis means I cannot include it. And 3 goes to infinity, right? This number line is going to go on and on and on forever. And just as a rule of thumb, the infinity symbols have to have parentheses. So that would be your answer in interval notation, right? So we'll give you some examples and graphs with domain and range so we can put the two together. Okay, so with interval notation and domain and range, I want to draw a graph with a range of, let's just say, I've got a different sheet here, -infinity to 2. And I can be equal to 2. And then a domain of -infinity to, let's say, infinity, right? Which is basically saying everything goes. -infinity to infinity means everything is included. Everything from the lowest number possible, -infinity, to the highest number possible, infinity. So it's another way of saying all real numbers. So let's see if you can pause the video and try and draw a graph on your sheet that has a range of -infinity to 2, so y values from -infinity to 2, and x values that go left and right forever, -infinity to infinity. All right, so you can resume the video. Let's see if we can draw one here. There's plenty of them that could exist, but one that comes to mind for me is an absolute value, which is a V shape. So it has a range of -infinity to 2, right? So the range is the y value. Here's -infinity. So it's going to go up to y is equal to 2, which is right there. And it can't go any higher than that because 2 is the highest I can possibly get to. So what I'm actually going to do, I can't stop it. And if you're thinking, why can't you stop it? Because the domain has to be everything, right? I have to have numbers left and right forever. So I'm going to put an arrow on the end of this, but all I'm going to do is reverse direction and say, okay, if I go like this, now I have a graph that goes left and right forever, and I have a graph that goes up to 2, but it will never actually become bigger than 2. So if you can kind of see it, right, left and right forever, right, this arrow goes left forever, this arrow goes right forever, also goes down, but it's still going right. And then range, okay, yes, I have graph from -infinity all the way up until I hit 2, and nothing, I have no range up here. And I'm never going to, because those arrows are going to continue down forever. Right? So that would be a good example of one. And you could have done something totally different that still might work. Okay, the second one we're going to do is do a range of, let's say, we'll go 0 to 5. and we'll include 5 and we'll include 0, and a domain of, well, we could just do a domain of, let's say, -2 to 2. And that's all that we'll do for this one. So with this one, if you think about a domain of -2 to 2, right? This is -2 here, and this is +2 here. So all of my x values have to be between here and here. I can't go outside any of these values of x. The range has to be between 0, so y values of 0, of 1, 2, 3, 4, and 5. So essentially, you just need to make sure it starts on the left side here, ends on the right side here, and then also includes these y values somewhere in there. So you could draw, I mean, a line or a segment is actually fine. I'll just do it in a different color, green. But basically, let me move it up a little bit. I'm just going to start at the top here and literally go to the bottom here. It doesn't even have to be a line, it can be any shape, but that works, right? The domain is between -2 and 2, so my x value is -2 to +2. The lowest y value I have is 0, the highest y value I have is 5, and everything in between is included. So that's one. It could have been a totally different shape. It could be a curve and, you know, hit those y values twice, like a parabola. That's fine. However you drew it, I'm sure it probably works, but that would be another example there. The last one I wanted to do is let's draw one with a range of -infinity to infinity, and a domain of the same thing, so -infinity to infinity. Right, so you can pause it, and when you think you have one done, resume, and I'll give you an example, but it could be totally different than yours. All right, so for this one, literally, if you just drew a line like this, it would work. There's a whole bunch of other things that work too. You could draw, you know, things that curve. You could draw things that, you know, more linear like this. However you did it, I'm sure it works, but just make sure, do you have x values over here? So this is -infinity, right? And if I look at the line, or even this one, yes, I do, right? They're just down here, right? The line would be over here. You know, I keep going left, and I'd still have this line go left forever. This line's going to go right forever. So that's my domain of everything. And then the range, the lowest, right? -infinity is down here, right? I have y values down here. This line will continue down just as much as it continues left. And this one's going to continue up to +infinity as it goes to the right too. So that kind of takes care of both domain and range. Okay. All right. So what we're going to do now is look at specific functions and their domains and ranges. It's not something that you're going to have to know specifically exactly what they look like for now, but just kind of get used to the fact that they will have specific domains and ranges. All right, so we have a denominator cannot be equal to what when you have a fraction? Well, the denominator can never be 0, right? Because if a denominator is 0, the fraction is what we call undefined, right? And that would be a problem. We can't have anything undefined in math. So this is actually one of the functions that does have a domain restriction. You cannot plug anything in for x if it would create a denominator of 0, right? And these are what we call rational functions. They're essentially fractions. I hate that word fractions, though, because if you have x over 2, right? If I have y is equal to x over 2 plus 1, there's a fraction. It must be rational, right? It's not rational. That is linear function. It's definitely not a rational function because it's the same thing as 1/2 x plus 1. Slope of 1/2, y-intercept of 1, that's it. So be careful with that word fraction, even rational. The x coordinate has to be on the denominator for it to be considered one of these. Otherwise, it's probably still linear. Okay, so basically the denominator cannot be 0. So if we look at this one, 5 over x minus 2, you can probably do it in your head, but basically all that you have to do to solve it is say, okay, x minus 2, that's the denominator. The denominator cannot be equal to 0. And that's kind of how you solve it. And then you solve it like a regular equation. You add 2, and you get x cannot equal 2. That's the domain. Now, that's set builder notation, so you couldn't leave it like that. So your domain would have to be going to get rid of this. All right, your domain, we said x cannot be equal to 2. So you're going to think about how could you put that into interval notation, right? So the domain, which is just for D, you say, okay, well, what could it be? Could it be everything left of 2? Yeah, so it's negative infinity until we hit 2 because we can't equal 2. And since we can't equal 2, we have to use a parenthesis. And then it's also in union with everything that's bigger than 2. So it starts with 2 but can't equal 2 all the way to infinity. Seems like a really long way of saying what was in the green, but that's how you put it in interval notation. So the parentheses are showing that it could not be 2, but it could be everything left of it and then everything right of it. And notice again how we started with negative infinity and work our way towards positive infinity. Start with the lowest, end with the highest. The range is tricky, but it's pretty much just a rule for rationals, at least at this point. The range, again, is what results, right? So depending on what I plug in for this, what kind of numbers result, right? You can get really, really small numbers if you plug in a really big number for x, like 5 over a million is going to be something really, really small. You can actually also get really, really big numbers. If you plugged in like 2.0000001, you get 5 over 0.0000001, which is going to be a huge number. But there is one number that you're never going to get, and if you can tell, that's great. It's actually 0, right? Because the only way for a fraction to equal 0 is if the numerator is 0, right? If the denominator is 0, it's undefined. That's something totally different. So the only way for a fraction to be 0 is if the numerator is 0, and if you looked at the numerator, it's the number 5. You can't change that. It's not like it's 5 plus x or 5 times x. It's just 5. So it's actually the only number you're never going to get from a fraction. So it's negative infinity to 0, and then union with 0 to infinity. It's the only number, again, that you're never going to get. Just like x couldn't be 2, y cannot be 0, or f of x cannot be 0, ever. Right? And if you had if you wanted to draw a picture, essentially what it is, I'll try and get it on the graphing calculator. But it's 5 divided by, oops. And you always want to use parentheses for denominators and numerators. X minus 2. And if we graphed it, you'll see that I have numbers all the way to the left, so negative infinity, and then we don't quite hit 2, and then we go from basically 2 all the way to infinity for the domain, and then you can see the range. I have numbers, whoops, got killed. But basically, I had numbers down to negative infinity, and then, it's kind of like this kind of a shape here. And these lines went forever and ever. And then after 2, it got really, really close. It gets close to 0, but doesn't actually touch it. Kind of that's smoother, but that's kind of what it looks like. So you have domain, yes, 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 but then at 2 you don't, and you never could. And then after 2, yes, all the way to the right. And then the range was negative infinity, yes, this arrow goes down forever, up until 0, but you never actually hit 0. But then right above 0 you do, all the way up to infinity. So it's kind of how it matches the graph. Okay, absolute values, just a different type of function that we're going to look at. So we have y, or f of x, is equal to x plus 1. Inside the bars can be anything, right? You can plug in whatever you want for x. So inside you can have positive numbers. You can have negative numbers inside. You can even have 0 inside, right? But the result, right, the range, the result of an absolute value is always going to be something positive, or it still could be 0, right? You could have the absolute value of 0, which is just 0. So, we want to look at domain and range with these functions as well. So for domain, again, it's what can I plug in for x, right? You can plug in whatever you want. There's no denominators here that you have to worry about. Absolute values can be anything. Not the result, but you can plug in anything. So we're going to say domain is all reals, which is just negative infinity to infinity. Everything's included, right? Even if I plug in negative 1 right there, it results in a number. That number's 0, but that's nothing special. It's still a number that you can get. It's not like it's undefined, which is a problem. Now, the range, especially just for this one here, but for most absolute values, is what results, right? So what's the lowest thing that could result from an absolute value? Would be 0, right? And you could be 0, right? If I plugged in -1, I get 0. So it starts at 0, and every other thing that would result from an absolute value would be something positive. So it started at 0 and could go all the way up to infinity if you plugged in infinity for x. So that's kind of the domain and range. And then if you look at a graph of it, you can try the graphing calculator again if it works. But essentially what you're going to see is a graph that justifies those domains and ranges. All right, so I'm going to do absolute value of x plus 1. And if I look at the graph, right there is my graph. So what you can see here is, do you have x values over here? If we're looking at domain, right, we're going to look all the way to the left because these things have arrows. Right? Do I have graph over here? Yes, 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 yes. Everywhere from left to right you have graph, which just means domain is negative infinity to infinity. It's just showing you the algebra. It's showing you the visual to the algebra, which just said I can plug in whatever I want. Right? And then when you look at range, see if we can get a range here. Okay, range start with negative infinity for y's. Like, do you have any y's down here? No, you don't. And if you look at the way the arrows are going and where the absolute value's vertex is or the bottom is, you never will. You're never going to have range down here. But where does it start? Right? It starts right there at y equals 0, and then it goes all the way up to infinity. Right? Those, either side is going to go up to infinity, so that's kind of why we get the answer algebraically from 0 to infinity, because those are the kinds of numbers that result from absolute values. All right, so that's one example of that one. The last one I really want to do today is square roots. So I have, we just finished radicals a little bit ago, so we're going to do square roots. We're going to do the square root of x minus 2. So this is another one with a domain restriction because there could be a problem, right? We're always going to assume that inside the radical has to be a positive number, or it could be 0. But when we're thinking about these in terms of graphs, we can't really graph imaginary numbers. So at least not yet. You will in calculus, but so we don't want anything like that. So we need to plug in values of x that only create positive numbers or a 0. But anything that creates a negative under the square root, right, a negative radicand, would be a problem. So we want to avoid those. So in this case, and then it says, it should also say what kind of numbers result from square roots. Only positive numbers result, right? If it gave you a plus and minus, right? If it gave you plus and minus on the outside to start with, then you could have negative and positive roots. But if it doesn't give you that, you only assume that it's a positive square root. So we're only looking at positive results. Or again, it could be 0. If you get the square root of 0, that is just 0. So let's take a look at domain, right? For this case, you might be able to do it in your head and just say, okay, x minus 2, I got to plug in a number that's bigger than 2 or equal to 2. That is your domain. But what you can do is just look at the radicand and say, okay, it's x minus 2. What kind of numbers does x minus 2 have to result in? It has to be bigger than or equal to 0. Because if my radicand, which is x minus 2, is bigger than or equal to 0, I'm okay. So you'd add 2, you get x is greater than or equal to 2. And that's your domain. The problem is that set builder notation, you need to put in interval notation. So you say, okay, the lowest it's going to be is 2. And since it's greater than or equal to 2, the highest it's going to be is infinity. And that's it. And range, very similar to absolute values, what kind of numbers result from radicals? Like we just said, we're looking at only positives or 0. So the lowest is going to be 0, and that's included because the square root of 0 is 0. So that could be a result, and it could be all the way up to infinity. If you plug in 1,000,000, you're going to get a really big number underneath. So this graph, right, if we graphed it, I'm just going to get rid of this one. All right, we're going to do the square root of x minus 2. And when we look at it, that's the graph right there. Does it look like your domain and range are all set? It should, right? Because we said that the domain had to be bigger than or equal to 2, which, right, that's the x value of 2 right there, and you have only x values that are bigger than or equal to 2. So that's everything greater than or equal to 2. We're good for domain. Notice how over here you have no domain, right? There's no numbers to the left of that 2. But it does include 2. That's kind of hard to see on a graphing calculator. But that point right there at x equals 2, that is actually included. It's like a closed circle. And then range, we said the range was 0 to infinity because those are the kind of numbers that result from square roots. If you look at the graph, right, this arrow is going to go right and also up forever. So there's no range down here, which is negative infinity all the way up until 0. But then it does include 0 right there, and it goes up to infinity. Again, it looks like it levels out, but it doesn't. It continues to go up just at a very slow rate. Okay, so those should basically just be confirming your answers that you already got from the classwork. What you can do for square roots, if you have problems trying to figure out where the domain is, we do this number line test. I don't think that most of you need to do it, but it's definitely helpful for certain problems too. So again, you can just take the radicand and say, okay, 2x minus 13, must be greater than or equal to 0. And you would add 13, you divide by 2, and you get x is greater than or equal to 13 halves. And that's it, right? So, you'd have to put that in set builder. In interval notation, you'd be done. But there's a number line that you can do for other types of problems, like this one, right? So here, the problem is underneath you have a quadratic. It's x squared minus 9. So you could say x squared minus 9 is greater than or equal to 0. You get x squared is greater than or equal to 9. And then you take the square root. And when you take the square root, right, we created the square root. Whoops. Oh, I'm going to have to redo that. So x squared minus 9 is greater than or equal to 0. X squared is greater than or equal to 9. X would be plus and minus here because we took the square root. So that means we have to account for positive and negative. And you'll get x is greater than or equal to plus and minus 3. It doesn't really work that way when you have two different numbers that create it. So we have positive 3 and negative 3 that would both give me 0. But it's not like x is going to be greater than both of them. So we do this thing called a number line, where instead of solving it greater than or equal to 0, if you know that it's going to be 2 answers, right, you could say x squared minus 9 just equals 0. Do the same math. You get x is equal to plus and minus 3, but you can put those numbers onto a number line, negative 3 and positive 3. You can put them on a number line, and that way you can see what types of numbers work, right? So these are x values here. And actually, both of these x values are okay in terms of the domain, because if I plugged in negative 3 or positive 3 in for x, I get a result of 0, and that's fine. The square root of 0 is 0. It's a number. It's not imaginary. It's okay. So I'm going to do closed circles there. And then what you can do is just try numbers around those. Like, so if I try to number in between negative 3 and 3, like maybe 1, see if I could plug in 1 into the original. And if you see, you couldn't, right? Because it would be 1 squared minus 9, which would be negative 8. I don't want negatives in my radicand. So anything in between, not just 1, but anything in between those numbers wouldn't work. And then try a number like bigger than 3, so like a number over here, like 5. 5 squared is 25, 25 minus 9. Okay, it's 16 is actually a perfect, but as long as it's positive, it's okay. So that would work. And a number less than negative 3, like negative 100, make it easy. Right, negative 100 squared is going to be something very big, minus 9. Still going to be positive, it works. So that number line would give you your domain just in a little bit more intensive way, because you had two different numbers that when you set it equal to 0, you got two different answers. So you might want to put them both on a number line and then test, instead of just saying greater than or equal to both of those. So this domain would actually be, if you look at the number line, starts at negative infinity and works its way up into negative 3. and it could be that number, and then it starts back up. So we're going to say or union with positive 3 to infinity, right? But it doesn't include anything between negative 3 and 3. And then the last one would be this one. The range for this one, I didn't do it. Same thing as it always is. It's still 0 to infinity. Because it's a square root, what kind of numbers result from square root? 0 to infinity. This would be the last one that we'll do, and then you'll work with your processing partners to do some of those classwork problems. But I'm going to do kind of the same thing. I'm going to take the square root and say, okay, 5x minus 3. It's only going to be one answer from this one. 5x minus 3 greater than or equal to 0. So I'm going to add 3, divide by 5, and I get 3/5. So that's my domain. Right? I'm done there. I didn't get two answers, so you don't have to put it on a number line. You can, right? You could do 3/5 on a number line and just figure out that anything bigger than that works. Or you could just do it this way and say, okay, the domain starts at 5 or 3/5, and it could be that because if I plug that number in, I get 0, and the square root of 0 is fine, as long as it's not negative, and it goes all the way to infinity because it's greater than or equal to that number. The range, right, we just said the range for square roots is going to be 0 to infinity, right? It has to be positive or 0. But when you think of the range, it's the result of the entire thing. So the entire thing also includes this plus 1 right here. So if the range of this part is 0 to infinity, and then I add 1 to that, you can kind of see what the range would actually become now. Instead of 0 to infinity, it's actually 1 to infinity, because the range is a result of the whole thing. So if the square root, the lowest at the square root part is going to be a 0. The lowest that the whole thing is going to be is 0 plus 1, so it would be 1. All right, just to show it on a graph. Whoops. Okay. So that one was 5x minus 3 plus 1. So we do second. Whoops. 5x minus 3. And then on the outside, we're going to do plus 1. And if I had to look at that graph, it's that blue one. That should kind of confirm our answers, right? The range, so the y values, start right there at y equals 1 and go up to infinity, because this is going to continue to go up, right? And then the domain, if you kind of notice, right, it kind of looks, it's hard to tell, but that right there, it starts at 0.6, right, which is the exact same thing as 3/5. And it goes 3/5 all the way to the right, so it's 0.6 to infinity for the range. Okay? So now what I want you to do in processing partners, or just do it in the people near you, because I'm not sure how much time you have based on how many notes you took. But I kind of want you to just pick 4, or however many you have time for, and do those ones on your classwork. And then your homework, again, it's in the 1.B or 1B folder on Schoology. It's just a worksheet.